So what are we talking about today, Sheesh?
Yeah, Nikki, so the thing we should talk about is quite important for RISC-V is memory subsystems. So they are a real nightmare for verification. And I want to talk about some example scenarios and problems that we encounter routinely and what we think we can do with formal. So imagine this is a RISC-V processor and this got a little this is where you have the fetch, decode, and all of the business, and then it interacts with a memory management unit, and that generates a translation of the addresses. And let's say they go to a cache, and as you know, modern processors and SoCs all have caches. So the first line of lookup is go and make a request for a read or a write into a cache. And what's happening here is that based on whether or not the requested data is in the cache, you can have a hit or a miss. Now, hit is easy. If you find the data, you can return it back. So this would typically happen with a load request. So when you load a word, it will load the cache line and will put it back into the register. So what we're really doing is we are actually verifying the correctness of loads and stores. This is what we are trying to do here in an app sense. We have this formalizer app, we are running the check for load and store. And if the data is found, the cache will return the data back and it will be committed to the register. But if there is a miss and the data is not there in the cache, then typically what happens is the request goes to the memory, and from the memory, the data is returned back to the cache, and it is then returned back to the register files. But it doesn't all happen in one frame. So what happens is for every time you get a miss, all the misses are getting tracked in what is called a miss queue. And the miss queue tracks all of the outstanding misses. And once you've got the data back from the memory, there is some logic that comes back to the miss queue to tell the miss queue you can let these lines go away, and we've got the good data back, and the data can be returned back to the cache. But as you know, modern caches are quite complex because they're not only just several level, but you have this concept of dirty lines and valid lines. And if there is any problem that can happen from the way these components are interacting, you will end up having a bug. So typically what happens is if you have a problem in wrong things going inside the misqueue or early evictions out of misqueue, you can have a problem. The data returned from the memory that goes back to the cache must validate or invalidate the cache lines correctly. And another thing that's quite important to understand is that normally we think of loads and stores as simple reads and writes, but actually there are lots of different types of loads and stores. So they are not just cacheable loads and stores, but you also have what is called atomic loads and stores and bypass loads and stores. So there's a lot going on, and it's very easy to get these things wrong and have bugs in silicon. So I'm going to show you a bug that we found in one of the RISC-V cores in the cache subsystem, but let me do this with a real waveform, shall we?
Sure, let's do it. So what are we looking at?
Okay, Nikki, so on the board I was telling you about these cache type designs. So here's what is happening. You've got a load word that has been issued from the processor for an address A, and this basically doesn't get a hit in the cache, so it goes as a miss, and it starts to get recorded in the miss buffer. And the request for the read has gone to the main memory, and the memory is able to find the data value D1 for this load word request, and it is going to then supply this value back to the processor, and everything would be fine, except that what you have is that after this load word actually was issued and these requests had been made to the memory for a read, you had another store word of a different value D2 to the same address. So the store word now goes and overwrites the value of the address A in memory, and it tells the processor that actually, oh yeah, the data has come back for a load word for address A and the value is D1. That's all good because the load was ahead of store. So it is meant to get the value D1. The problem is you've got another store coming along, and that has basically sat there with the request having been passed to the memory and an update has happened. So when you get another load coming in for the same address, actually what is meant to happen is that this store, which was a bypass store and was working directly in the memory, should have rendered the cache line to be invalid. But basically, there is a bug in the design, and this bypass store does not render the cache line in an invalid state for this address A. So when you have this third load come in, it goes to the cache for a lookup, and because the cache line is not rendered invalid, it picks up a stale value of D1. What it should be really doing is it should be saying, okay, I have an invalid cache line. I should be going to the memory to pick up the latest value, which is the value D2. But instead of picking up D2, it picks up D1 and then returns the values, which is the stale value, back to the load. So these kind of bugs can be very easily missed in an environment where you're running millions and millions of test cases in dynamic simulation. With formal, we can catch these bugs really easily because we will write one assertion which is on the correctness of the load and another one on the store, and they will pick these bugs. So that's what is happening. Does it make sense, Nikki?
Yeah. So it is the bypass store to the same address as a previous load that should have rendered the cache line as invalid, and it isn't doing it, right?
Correct.
Okay, so then when a latter load comes along for the same address as the previous two instructions, it picks up the stale value from the cache line as opposed to the main memory, which was holding the most recent update from the store.
Correct. Yes,
I
you've
see.
captured it absolutely correctly.
Thank you.
Perfect.